Hello, y'all. Barely Berry Jr. back and continuing where we left off with our reading of classical dynamics. Uh, we have proper one click. There we go. It's playing now. Good. All right. Make sure this is showing live. Good. So we'll continue where we left off in the reading. We were at the rules of problem solving in the equation of motions of a particle. So we have problem solving techniques. Sketch what's going on with forces, velocities, etc. Write the givens, write useful equations, write what you're trying to find, note what you're trying to find, strategize, which algebra, integration, derivation, etc. And lastly, input the values and solve for what you need on page 55. So let's first consider the problem of a block sliding on an inclined plane. So block inclined plane, a classic problem. So we have a block like so, that's inclined. This is a right angle. This is the angle theta. And the mass is 100. So the mass here equals 100 grams. Right? So we have all the forces added here. We have friction going up. Y'all notice this. We have the normal force going away from the plane of the block. We have the force of gravity, which is going straight down. But this will be divided on the block. So some of it will be going perpendicular into the block. And this angle will still be theta. This will be a right angle. So cosine of theta, Fg, cosine theta is the force going in that direction. And in this direction here, we have Fg sine theta. Which is the opposite. Right, so that's right. And the way the coordinate system is, we have y going straight up, positive y, and x is going down the ramp. So the coordinate system is on the ramp. All right. This is example 2.1. So if the block slides without friction down a fixed inclined plane with theta equals 30, what is the block's acceleration? So two forces act on the block. The gravitational force and the plane's normal force, if we ignore friction. So actually, example 2.1, friction equals 0. So now we only have the normal force and the force of gravity. The block is constrained to be on a plane, and the only direction a block can move is the x direction up and down the plane. Because it can't go through the plane and it's not going to float up since there's no force going up that's greater than the force of gravity in that direction. We take the plus x direction to be down the plane, which I have there. The total force net is constant and becomes F net equals Fg plus N. So the total force is acting on the block is the normal force and the force of gravity, since we're ignoring friction. And that means we can say MA, F net is MA equals Fg plus N. Right, so good so far. This vector must be applied in two directions, x and y, perpendicular to x. The component of force in the y direction is 0 because no acceleration occurs in this direction. The force G is divided vectorially into its x and y components. And this is equation, a modified equation 2.8, but close enough. So this is going to equal Fx, which is the x direction, plus Fy plus Nj. So Fx is going up and down the ramp, and Fy is balancing the normal force. So we know that Fy equals negative N. So those are going to equal 0. So we have Mx dot equals Fx, which we know is going to be Fg sine theta. So this equals Mg sine theta, and M can cancel as the mass is the same. And thus we have x dot equals G sine theta equals G sine, in this case, 30 degrees. Right? Sine of 30 degrees, if I remember my unit circle, But we know that this is 0, this is 90, this is 30, 45, 60. We know this is square root of 2 over 2 for both of them. We know this is 1, 0. This is 0, 1. So this would be square root of 3 over 2 uh, half would be 1 half 3 over 2. So sine of 30 degrees is 1 half. So x double dot equals g over 2. I think there's a typo here. Which is 4.9 meters per second squared. Therefore, the acceleration of the block is constant. We can find the velocity of the block after it moves from rest a distance xo down the plane by multiplying equation 2.11. This is equation 2.11 by 2 and integrating. By 2 dot and integrating. Why would we multiply by 2x dot? Take a look and see. They're saying we can find the velocity after it moves down from rest a distance by multiplying equation 2.11 by 2x dot. We have x dot dot equals g sine theta. I'm going to multiply both sides by 2x dot, 2x dot. So 2x dot, x dot dot equals 2x dot g sine theta. So this is the same thing as 2x dot d over dt, x dot. I think this would be a horrible way to get this answer. And the book has x dot squared now, even though we're only taking the time derivative of one of them. And this seems to be a horrible way to get the velocity. And I hate this book because they're definitely not clear about what they're doing in between these two spots. Sometimes author seems to be like these books are written just to make the author feel smart, uh, rather than to actually educate the reader. Why don't we do it the way I would normally do it and say this is A equals G over 2. So dV over dt equals G over 2. So dV equals G over 2 dt. Then I can integrate this, and I can say V of t equals V over 2 t plus V naught. Or if I also do this, keeping the sign and go from here, we can say A equals G sine theta, dV over dt equals G sine theta, dV equals G sine theta dt. And then we integrate, and then we have Vt equals G sine theta t plus c. Still not sure why they would multiply by an extra velocity. Um, and that t equals 0, v equals 0 if it's starting from rest. So 0 equals G sine 0 G sine theta 0 plus c. So c equals 0. So Vt equals G sine theta, or GT sine theta. Still looking at this integral at what they did. I don't see why they did that. Uh, Saying we can find the velocity of the block after it moves from rest at a distance xo down the plane. So why don't we integrate this one more time? Dx over dt equals gt sine theta, and dx equals gt sine theta dt. So if I take the integral of both sides, we have xt equals 1/2 gt squared sine theta plus x naught, and at t equals 0, t equals 0, x equals 0, since I'll define it that way. So x0 equals 0 equals 1/2, well, that's going to be 0 equals xo. So xo equals 0, which adds up. So xt equals 1/2 gt squared. Times sine theta. So that will still cut the speed in half. At xo, it moves that far. I can solve to get the time for xo and insert that time. So we can say t equals 2xt over g, the square root of that, g sine theta. So I just multiply the other side by 2 divided by g divided by sine theta and took the square root. So if I wanted the velocity, I'll call this t star. So if I wanted the velocity at t star, that will be g 2x of t. And if I wanted t star at xt equals xo, so this would be 2xo g sine theta sine theta equal 2g xo. G is cancels as well. So the gravity cancels and the sine cancels. 2xo is going to be the speed. That can't be right. Oh, the square root. I forgot the square root on that. All the units are correct. So it would be Well, to simplify this, it would be 2g squared xo sine of theta squared over g sine theta. If I bring the g and the sine into the square root, so that'll be 2g xo sine theta, square root of that. And what do you know? We have what they have. We have the square root of 2g xo sine theta. So that's v at t star. So still not sure why they did what they did, but we end up with the same result. So this is the velocity after the particle move distance xo. And as we can see, this matches the book answer. VO equals 2g sine theta xo. Let's look at this again. So we want the question is, what speed does the block have after moving xo distance, right? So what I did was do our normal integration. Those who've been watching my channel or other channels know about this integration of acceleration to give us, oh, one moment. So those who've been watching me know about this process of integration to get the position and velocity equations. So we know from our equation of motion for the block that our acceleration is 1/2 the gravity because of the 30-degree angle. I did my integration of that. Got my v of t, where v not equals 0. Integration of that, got my x of t. So this second equation gives me the position of the block at any given time, given its velocity, and the gravity imposed upon it at that angle. So I wanted to find the position at a certain t. So I'll solve this for t and say the position after a certain amount of time, and we'll call that x at that certain amount of time xo. So the time to pass to get to xo is that amount of time given our position equation. So then I plugged in this time into the velocity equation that we calculated earlier. So now we have the velocity at this time asterisk, which is the amount of time to get to the xo, the position that we want. Plugging that time in and simplifying, this is the velocity after time t asterisk to get us to the position x naught. So I can pick my x naught, whatever I want it to be. That'll give us meter squared over second squared, 2 sine theta, and that'll give us the velocity at that given x naught, which is the velocity of the block after it moves from rest a distance x naught. All right, easy enough. So this is a good example of how We don't have to necessarily stick with the book method of solving things. If we understand the basic process of our own method, and I would say this integration process is universal, and we simply applied it, and I guess it's technically more roundabout. Apparently, they did some multiplying by 2x dot and taking the derivative of the both of the x dots, even though only one of them were initially having the derivative of it. So I'm not sure about the nature of how they did this. Look at that, they have dx dt on the right. Oh, ain't that something? I think I see what they did. Apparently, I guess I have to get the answer a different way to see. No, it still doesn't make sense because they have two x dot dot. So the x dot is d dt x dot. But why would you then take the derivative of both of them? So yeah, there's just some math there I don't understand. But we were still able to get the position of the block, give me the speed of the block after a certain velocity by doing it the other way. So I feel good about that. Example 2.2. And actually, I'll go ahead and take a break. We'll take a break here, and we'll come back with the next example.